Long before humans understood what fire truly was, they depended on it completely. A flame meant warmth against the cold, protection from predators, and the first taste of cooked meat that helped reshape the human brain. Yet for hundreds of thousands of years, no one asked the question that mattered most. What was fire actually consuming? Why did it brighten when a breath crossed the embers? And why did it die when sealed inside a jar? The answer was invisible and weightless, floating through every forest and every human lung. It would take civilization thousands of years to notice it. In ancient Greece, philosophers built entire worldviews around four visible elements: earth, water, fire, and air. Empedocles taught that these building blocks explained all existence. Aristotle refined the idea further, describing fire as a substance that naturally rose toward the heavens. It was elegant, intuitive, and wrong in a way that would quietly delay chemistry 4,000 years. Air, in this ancient framework, was treated as passive and uniform, a simple backdrop for the true drama of fire, water, and earth. Elsewhere, different civilizations arrived at a similar intuition through different paths. In ancient China, physicians spoke of qi, a vital breath energy flowing through the body. In India, yogic tradition described prana, the life force carried on every inhalation. These were not chemical theories, but something closer to philosophy, born from simple observation: stop breathing, and life ends. Across cultures separated by oceans and centuries, humanity kept circling the same unspoken truth without ever naming it. Then came the alchemists. Working in dim rooms filled with charcoal smoke, medieval experimenters pursued transmutation and immortality, chasing gold from lead. Their goals were mystical. Their methods, almost by accident, were becoming something more scientific. They learned to collect vapors, to seal flasks, to observe how gases behaved when trapped. Within these smoky workshops, the earliest tools of experimental chemistry slowly took shape. By the 17th century, a quieter revolution was underway in England. Robert Boyle, working with a mechanical air pump inside his Oxford laboratory, placed a burning candle beneath a sealed glass bell jar and slowly drew the air out. The flame did not simply flicker. It shrank and extinguished, as though starved of something specific. Boyle repeated the experiment with a small bird in place of the candle, and the result was strikingly similar. Whatever sustained the flame also sustained the breath of a living creature. Two mysteries, fire and life, were converging toward a single hidden cause. Around the same period, German chemist Johann Joachim Becher began weighing the ashes left behind after combustion, noticing that burned material lost both mass and character. His successor, Georg Stahl, formalized this observation into an influential theory. Burning substances released an invisible fire essence called phlogiston. It was a bold, organizing idea that would dominate European chemistry for the better part of a century, explaining flame, rust, and decay with remarkable consistency. But theories, however elegant, eventually meet evidence that refuses to fit. In quiet countryside laboratories across England, patient experimenters were about to isolate a substance so vigorously alive with combustive energy that it would force an entire discipline to reconsider everything it thought it understood about fire, air, and the invisible force sustaining both, flame and breath. The candle, the glass jar, and the burning lens were waiting. If phlogiston theory was going to be tested, it would need better tools. In 1727, the English clergyman Stephen Hales built one of the simplest and most consequential devices in the history of chemistry: a trough of water designed to capture gases rising from heated materials, rather than letting them vanish into the open air. For the first time, invisible substances could be gathered, examined, and compared. Hales discovered something unsettling to the old world view. Air was not one thing. It was a family of distinct gases, each behaving differently, each waiting to be named. In Edinburgh, the chemist Joseph picked up where Hales left off. Heating a chalky mineral called magnesia alba, he collected a gas that snuffed out flame instantly and clouded clear limb water within seconds. He called it fixed air, what we now know as carbon dioxide. It was proof that an entire hidden chemistry of gases lay beneath the ordinary atmosphere everyone breathed without a second thought. In London, Henry Cavendish went further still, isolating a gas so flammable it ignited with a sharp flash the instant a flame touched it. He named it inflammable air, and weighed it with an obsessive precision that would soon become the hallmark of modern chemistry. Fixed air, inflammable air, ordinary air. The catalogue was growing, and with it, growing confusion. Phlogiston theory had never been designed to explain a world with this many kinds of air. And then came a problem phlogiston simply could not answer. When metals were heated in open air, they transformed into a brittle, ash-like powder called calx. According to theory, this process released phlogiston, the fire essence escaping into the surrounding air. But when chemists placed their calx on a precision balance, something impossible happened. It weighed more than the original metal, not less. If phlogiston was escaping, how could the leftover material be heavier than what it started from? Some theorists proposed, almost desperately, that phlogiston must possess negative weight, a fix that satisfied almost no one. Across London's coffee houses and scientific societies, the debate simmered. Younger chemists exchanged skeptical glances while older colleagues clung to a century of accumulated theory. Meanwhile, in a modest English rectory, a Unitarian minister with a passion for scientific inquiry had spent years quietly collecting his own jars of gas, testing candles, testing mice, corresponding with fellow investigators across Europe. His name was Joseph Priestley, and though he remained personally devoted to phlogiston theory, his instruments were about to reveal something that theory could never fully contain. By the summer of 1774, Priestley had assembled everything he needed: a burning lens capable of concentrating sunlight into intense, focused heat, a supply of reddish mercury calx, and a trough, not of water, but of mercury, since he suspected his next discovery might dissolve in water before he could ever observe it. On the morning of the 1st of August, sunlight poured through his study window. The lens was positioned, powder weighted beneath the glass. 2,000 years of scattered observation, from Aristotle's four elements to Boyle's flickering candle, were about to converge into a single, decisive afternoon. The powder began to shimmer under the concentrated sunlight, and thin bubbles of gas rose steadily into the mercury trough above. Priestley leaned closer, watching an inverted jar slowly fill with something entirely new. He lowered a glowing wood splint toward its mouth, expecting little. Instead, the ember burst into a flame so vigorous, so unmistakably alive, that it seemed to defy the ordinary rules of combustion he had spent years studying. He repeated the test. The result held. Whatever filled that jar was unlike any gas previously catalogued. Next came the mice. Priestley placed one inside a sealed container of his new gas, and the second inside an identical container filled with ordinary air. The contrast was startling. The mouse breathing common air weakened within minutes. The one inside Priestley's gas remained active for roughly 4 to 5 times as long. Driven by curiosity that bordered on recklessness, Priestley did something few scientists of his era would attempt. He inhaled the gas himself, later describing the sensation as his chest feeling remarkably light and easy. Working entirely within the framework of phlogiston theory, he concluded that this vigorous new air must be unusually free of phlogiston. He called it dephlogisticated air. Word of the discovery spread quickly through England's scientific circles, carried by letters crossing the Channel toward Paris. Priestley himself soon followed, traveling to France to meet the ambitious young chemist already transforming laboratory science through unmatched precision. Antoine Lavoisier. Over dinner in Lavoisier's elegant townhouse laboratory, Priestley described his mercury calx experiment in careful detail. Lavoisier listened, with the quiet intensity of a man recognizing something far larger than his guest yet realized. Within days, Lavoisier's assistants were preparing to repeat the experiment themselves, this time with instruments capable of measuring every gram, every fraction, every subtle shift in weight. Priestley returned home to continue his own investigations, testing his new air against metals, plants, and flame after flame, each trial reinforcing its extraordinary combustive power. Yet even as evidence accumulated against his own theoretical framework, Priestley remained committed to phlogiston until the end of his life, a striking reminder that even brilliant minds can struggle to abandon the ideas that shaped their entire careers. His discovery, however, had already escaped his control. It belonged now to the wider scientific world, ready to be reinterpreted, renamed, and ultimately understood in a way its own discoverer never fully accepted. But Priestley was not alone in reaching this threshold. Nearly 2 years earlier, in a modest Swedish apothecary shop, far from London's grand laboratories, another chemist had already produced remarkably similar results, working in near total isolation, delayed by publishing setbacks that would cost him the historical credit his careful science deserved. In the small Swedish town of Köping, Carl Wilhelm Scheele spent his days behind an apothecary counter, mixing remedies for ordinary townsfolk who had no idea their pharmacist was quietly rewriting the boundaries of chemistry. In the back room of his shop, using little more than saltpeter, manganese dioxide, and a modest collection of glassware, Scheele achieved something remarkable. He isolated the very same gas Priestley would later celebrate, and he did it years earlier. He called it fire air, a name that captured, with plain accuracy, its startling ability to intensify flame far beyond what ordinary air could sustain. Scheele's methods were every bit as rigorous as those practiced in London or Paris. He tested his fire air against glowing splints, watching them roar into brightness. He compared this effect on caged mice against ordinary air, observing the same striking pattern of extended vitality. He documented everything meticulously in a growing personal notebook, evidence of an extraordinary independent mind working almost entirely without the institutional support enjoyed by his continental counterparts. In 1774, he even wrote directly to Lavoisier, describing his discovery in careful scientific French, letter that arrived in Paris before Priestley's own famous announcement ever reached the city. Yet history rarely rewards discovery alone. It rewards discovery combined with timing, connection, and publication. Scheele's manuscript, eventually titled Chemical Treatise on Air and Fire, sat delayed 4 years by ordinary printing house backlogs, entirely unrelated to the brilliance of the science it contained. By the time it finally reached European readers in 1777, Priestley's dramatic public demonstrations had already captured the scientific world's attention, and Lavoisier's precise reinterpretation was already reshaping the field. Scheele's contribution, though genuinely foundational, would be remembered as parallel rather than primary. There was a darker cost to Scheele's dedication as well. Like many chemists of his era, he routinely tested unknown substances by smell and even by taste, a common but hazardous practice that exposed him repeatedly to toxic compounds throughout his career. Alongside fire air, he independently discovered chlorine, tungsten, and several previously unknown acids, an almost unbelievable scientific output for one provincial pharmacist working largely alone. But the cumulative toll of decades spent handling dangerous chemicals without protection would shorten his life considerably, a quiet tragedy behind one of chemistry's most productive careers. Scheele's story stands as a necessary counterweight to the more celebrated narratives of Priestley and Lavoisier, a reminder that scientific history is rarely as simple as a single dramatic breakthrough. Sometimes discovery arrives simultaneously, in different languages, in different social circumstances, deserving equal recognition even when history distributes credit unevenly. And it was in Paris, not Coping or rural England, that these separate threads would finally be woven into a single, unified theory. Antoine Lavoisier did not merely repeat Priestley's experiment. He transformed it into an entirely new science. Working within his meticulously organized Parisian laboratory, Lavoisier sealed mercury inside a glass retort and heated it patiently for 12 full days, weighing every component before, during, and after the reaction with a precision no chemist had previously attempted. When the numbers settled, they revealed something extraordinary. Nothing had been lost. The weight gained by the mercury calx precisely matched the weight of gas consumed from the surrounding air. Mass had neither appeared nor vanished. It had simply changed form. This single insight demolished the foundation of phlogiston theory. Combustion, Lavoisier realized, was not the release of a mysterious fire essence. It was combination, a substance in the air joining directly with the burning material. He proposed a bold new name for this substance, oxygen, derived from Greek roots meaning acid former, based on his belief that it played a role in forming every acid. That specific assumption would later prove only partly correct. The name, however, would endure permanently within scientific language. Lavoisier did not work alone. His wife, Marie-Anne Pauls Lavoisier, translated foreign scientific texts, illustrated laboratory apparatus with remarkable precision, and maintained detailed experimental records that historians still study today. Together, alongside collaborators including Berthollet and Fourcroy, the couple helped construct an entirely new chemical nomenclature, a systematic naming convention that finally replaced centuries of inconsistent, often mystical terminology. Lavoisier's landmark 1789 textbook, Traité élémentaire de chimie, organized this new understanding into a coherent framework that would define chemistry for generations to come. Lavoisier extended his insight further still, demonstrating alongside Armand Seguin that animal respiration functions essentially as a slow, controlled form of combustion, consuming oxygen and producing heat in strikingly similar proportions to an ordinary flame. Fire and life, it turned out, were not merely connected. They were, at a fundamental chemical level, expressions of the very same process. But Lavoisier's brilliance could not shield him from the turbulence engulfing France. His civic role within the country's controversial tax collection system made him a target once revolutionary fervor turned against the old financial order. In 1794, he was arrested, tried, and executed by guillotine. His request for time to complete an unfinished experiment coldly refused. The mathematician Lagrange later offered a devastating epitaph. It had taken only a moment to remove that head, though France might not produce another equal to it within a century. Lavoisier's life ended abruptly. His science, precise, measured, and permanent, would not. With phlogiston abandoned, chemistry could finally explain combustion in terms that matched observable reality. Oxidation, the direct chemical combination of oxygen with other elements, became the new organizing principle behind fire, rust, and decay alike. An iron nail left exposed to damp air would slowly darken and flake, its surface quietly combining with oxygen to form the reddish compound we call rust. A candle sealed beneath glass would dim and extinguish the moment its available oxygen ran out. The same invisible substance governed both transformations, whether violent and immediate or patient and gradual. John Dalton, working in Manchester, gave this new chemistry an atomic foundation, proposing that elements combined in fixed, predictable ratios, each atom possessing its own characteristic weight. Later, the Italian scientist Amedeo Avogadro proposed something subtler still, that oxygen exists in nature not as a lone atom, but paired, forming a single diatomic molecule. These theoretical refinements, though abstract, gave scientists the precise mathematical language needed to describe exactly how oxygen behaved during every chemical reaction, from a flickering candle to a rusting anchor chain. Careful measurement soon revealed oxygen's precise share of the atmosphere itself, roughly one-fifth of the air surrounding every living creature on Earth, with nitrogen making up most of the remainder. This simple percentage explained why fire behaved the way it did, why enclosed spaces grew dangerous over time, and why certain environments could support flame more vigorously than others. Understanding this ratio soon proved essential far beyond the laboratory. In coal mines across industrializing Britain, miners relied on a deceptively simple safety innovation: a lamp enclosed within fine wire mesh, its flame serving as a living indicator of breathable air. When oxygen grew scarce or dangerous gases accumulated, the flame changed shape or dimmed, offering silent warning long before human senses could detect the danger. It was applied chemistry saving lives underground, decades before anyone fully understood the biology of suffocation itself. Everyday life quietly absorbed this new understanding as well. Freshly cut fruit browning in open air, iron ships slowly rusting along their waterlines, matches igniting instantly through concentrated oxidizing compounds embedded in their tips. Each phenomenon, once mysterious, now belonged to a single coherent chemical story. Fireworks exploded in brilliant color through carefully engineered combinations of metal powders and oxygen-releasing compounds, transforming laboratory chemistry into shared public spectacle. Humanity had finally learned to read the invisible signature oxygen left on nearly everything it touched. Yet understanding combustion was only the beginning. The same gas responsible for flame, rust, and fireworks was also quietly at work inside every human body, sustaining a far more intimate and continuous kind of fire. Every breath a human being takes represents the final destination of a journey that began billions of years earlier and thousands of miles away. Air drawn into the lungs travels through a branching network of increasingly narrow passages before reaching the alveoli, countless microscopic air sacs, whose combined surface area rivals that of a tennis court, folded invisibly within the human chest. It is here, across membranes thinner than paper, that oxygen finally passes from inhaled air directly into the bloodstream. 19th-century physiologists, examining blood samples beneath early microscopes, noticed something visually striking. Oxygen-rich blood glowed a vivid cherry red, while oxygen-depleted blood settled into a darker, duller maroon. This simple color difference offered an early clue toward hemoglobin, the iron-containing protein within red blood cells responsible for binding oxygen in the lungs and releasing it precisely where the body's tissues need it most. Blood, it turned out, was not merely a fluid. It was a finely tuned transportation system, continuously ferrying oxygen from the outside world into the body's innermost cells. Physical exertion revealed this system's remarkable responsiveness. A runner's breathing quickens and deepens the moment muscles demand additional fuel, an automatic adjustment matching oxygen supply to immediate physical need. At high altitude, where atmospheric oxygen grows noticeably thinner, the same system strains visibly, a fact French physiologist Paul Bert investigated rigorously through carefully controlled low-pressure chamber experiments, laying essential groundwork for future mountaineering, aviation, and eventually space exploration. Perhaps no moment captures oxygen's biological significance more powerfully than a newborn infant's first breath. Within seconds of birth, fluid-filled lungs expand for the very first time, drawing in air and beginning an uninterrupted rhythm that will continue, largely unnoticed, for an entire human lifetime. Physicians attending these earliest moments gradually developed emergency techniques for restoring interrupted breathing, refining resuscitation methods that would eventually save countless lives following drowning, illness, and injury. Deeper still, 20th-century researchers discovered oxygen's role extending down to the cellular level itself, identifying mitochondria as the microscopic structures responsible for converting food energy into usable biological fuel through oxygen-dependent chemical reactions. This discovery completed a remarkable chain of understanding, connecting a single inhaled breath all the way down to the invisible machinery powering every individual cell within the human body. Oxygen was no longer simply air. It was the quiet engine of life itself, continuously running within every person, everywhere, without pause. Having transformed both chemistry and biology, oxygen's story was about to leave the laboratory entirely, reshaping the factories, furnaces, and industries defining the modern world. In 1856, English engineer Henry Bessemer stood before an enormous pear-shaped vessel filled with molten iron and ordered something that seemed almost reckless. Force air directly through the liquid metal. Oxygen within the rushing air reacted violently with carbon impurities trapped inside the iron, producing a dramatic shower of sparks, and within minutes, a dramatically purer, stronger metal we now call steel. What once required days of laborious refining now took only a matter of minutes. The Bessemer process did not simply improve metallurgy. It supplied the literal skeleton of the modern industrial world, the steel beams, railway lines, and structural framework that would soon define skylines and connect continents. Nearly 4 decades later, German engineer Carl von Linde achieved something equally transformative, cooling ordinary air until it liquefied entirely, and separating that liquid into its individual components through careful distillation. For the first time, pure oxygen could be produced not in small laboratory quantities, but on an industrial scale, compressed into steel cylinders and distributed wherever combustion-driven manufacturing required it. Pale blue liquid oxygen, extraordinarily cold and remarkably ordinary in origin, became one of the 20th century's most quietly essential industrial commodities. This abundance enabled entirely new manufacturing techniques. Oxyacetylene welding combined pure oxygen with acetylene fuel to produce flame temperatures far exceeding ordinary combustion, allowing workers to fuse steel plates together with the precision and strength previously unimaginable. Shipyards abandoned labor-intensive riveting in favor of continuous welded seams. Aircraft manufacturers adopted the same technology to construct lighter, stronger airframes. Glassblowers directed oxygen-enhanced flames toward molten glass, achieving faster, more precise shaping than traditional wood or coal-fire furnaces had ever allowed. Naturally, such power demanded respect. Industrial accidents involving improperly stored oxygen cylinders taught hard lessons about separating pressurized oxygen from flammable materials. Lessons eventually codified into strict safety protocols still followed in factories worldwide. Oxygen, chemists reminded engineers again and again, does not simply support combustion. It accelerates it dramatically, a property as useful as it is dangerous when mishandled. By the mid-20th century, vast air separation plants processed staggering volumes of atmosphere continuously, supplying purified oxygen to steelworks, chemical plants, and manufacturing facilities across the industrialized world. A gas once so mysterious that it eluded human notice for millennia had become an indispensable commodity, quietly underpinning skyscrapers, railways, and machinery around the globe. But oxygen's greatest transformation was still ahead of it, waiting inside the hospital wards, where its therapeutic power would soon begin saving lives directly. Medicine's relationship with oxygen began simply. A rubber tube, a compressed cylinder, and a patient struggling to breathe. In early 20th century hospital wards, physicians treating severe pneumonia discovered that supplemental oxygen delivered noticeable, sometimes dramatic relief, transforming an industrial gas into a genuine therapeutic tool. Canvas oxygen tents soon followed, enclosing patients within a concentrated therapeutic atmosphere long before precise flow regulators made such treatment safely routine. The First World War accelerated this development with brutal urgency. Soldiers exposed to chemical weapons suffered severe lung damage, and field hospitals scrambled to develop portable oxygen equipment capable of treating respiratory injury under desperate battlefield conditions. Aviation medicine advanced in tandem, as military pilots flying at dangerous altitudes required their own supplemental oxygen systems to remain conscious and effective during high-altitude combat missions, a direct extension of decades of accumulated respiratory physiology research. In operating theaters, anesthesiologists learned to combine oxygen with nitrous oxide in carefully calibrated proportions, enabling longer, safer, and more complex surgical procedures than previous, cruder anesthesia methods had ever allowed. Meanwhile, hospital nurseries began using oxygen-enriched incubators to support fragile premature infants, an innovation that saved countless young lives, though not without a difficult lesson. Excessive oxygen exposure, researchers eventually discovered, could seriously damage an infant's developing vision. It was a sobering reminder that even genuinely beneficial therapy requires precise, carefully measured administration rather than unrestrained enthusiasm. Later technological refinements transformed oxygen therapy from bedside improvisation into precision medicine. The pulse oximeter, small sensor clipped painlessly onto a fingertip, allowed continuous, non-invasive monitoring of blood oxygen saturation, becoming a standard fixture across virtually every modern medical setting. Sophisticated mechanical ventilators extended this precision further still, sustaining critically ill patients through carefully calibrated, continuously monitored respiratory support. Hyperbaric oxygen chambers, delivering concentrated oxygen at elevated pressure, prove remarkably effective for treating stubborn wounds and decompression injuries alike. Today, portable oxygen concentrators allow patients with chronic respiratory illness to maintain independent, comfortable lives well beyond hospital walls, while paramedics routinely administer emergency oxygen within the first critical minutes following injury or sudden illness. Yet significant disparities persist worldwide. In under-resourced clinics, healthcare workers still carefully ration limited oxygen supplies among patients who, elsewhere, would receive it without a second thought, an ongoing reminder that equitable access remains one of global medicine's continuing challenges. From battlefield desperation to routine hospital infrastructure, oxygen therapy's evolution reflects medicine's patient, hard-won mastery over this single, essential element. High above sea level, on the upper slopes of the world's tallest mountains, breathable oxygen grows perilously scarce, and the human body begins failing in ways no amount of determination alone can overcome. Early Everest expeditions in the 1920s carried heavy, unreliable oxygen cylinders into this thin atmosphere, learning through repeated hardship exactly how much supplemental oxygen extreme altitude demanded. By 1953, when Edmund Hillary and Tenzing Norgay finally reached the summit, refined oxygen equipment strapped securely to their backs made the historic achievement not merely possible, but survivable. The sky presented its own version of the same challenge. Early aviators flying at dangerous altitudes discovered that thinning air impaired judgment and consciousness long before it became immediately life-threatening, driving urgent development of aircraft oxygen systems, and, eventually, fully pressurized cabins that allow ordinary passengers today to cross oceans in comfort, entirely unaware of the thin, unbreathable air rushing past their windows at cruising altitude. Beneath the ocean's surface, engineers confronted an entirely different set of pressures. Early divers, connected to the surface through heavy brass helmets and air hoses, gradually gave way to self-contained underwater breathing systems, carefully calibrated to prevent dangerous decompression sickness during ascent. Modern rebreather technology extends underwater endurance further still, recycling exhaled breath while precisely replenishing consumed oxygen, a direct descendant of physiological principles first established through altitude and respiratory research decades earlier. Nowhere did oxygen's importance reach greater extremes than in the exploration of space itself. Spacesuit engineers designed sealed life support systems capable of sustaining astronauts entirely within the total vacuum beyond Earth's atmosphere, an achievement representing oxygen science's most extreme practical application. That triumph, however, came with a sobering cost. In Auxin 1967, a fire inside a sealed pure oxygen spacecraft cabin during ground testing claimed 3 astronauts' lives, a tragedy that forced engineers to fundamentally redesign cabin atmospheres and fire prevention systems for every subsequent crewed mission. It was a difficult but necessary lesson. Oxygen's life-giving power carries equally serious risk when carelessly contained. Today, aboard the International Space Station, sophisticated equipment generates fresh oxygen continuously through electrolysis, splitting water molecules to sustain astronauts through months-long missions without constant resupply from Earth. Researchers now study similar technology capable of extracting oxygen directly from the Martian atmosphere, preparing for humanity's next great leap beyond our home planet entirely. From mountain summits to ocean depths, to the vacuum of space, humanity's expanding reach has always depended on the same fundamental discovery, understanding precisely how to carry breathable oxygen into environments where nature never intended us to survive. Today, oxygen moves through modern civilization on a scale its early discoverers could scarcely have imagined. Vast industrial air separation plants process enormous volumes of atmosphere continuously, loading insulated tankers destined for hospitals, factories, and laboratories across the globe. Some of that purified oxygen travels farther than any 19th century chemist could have dreamed, serving as a powerful liquid oxidizer inside rocket engines, combining explosively with fuel to generate the tremendous thrust required to escape Earth's gravity entirely. Beyond these dramatic applications, oxygen quietly sustains countless ordinary systems most people never think twice about. Wastewater treatment facilities bubble oxygen through tanks to support bacteria that break down organic waste. Fish farms carefully oxygenate crowded tanks to sustain healthy aquaculture. Supermarket produce stays fresh longer inside specially sealed packaging that precisely balances internal oxygen levels. Automotive engineers rely on oxygen sensors within vehicle exhaust systems to optimize fuel efficiency and reduce harmful emissions, a small, largely invisible application of chemistry first understood over 2 centuries ago. Yet oxygen's most essential modern role remains exactly where it always was, within the living world itself. Dense tropical rainforests continue converting sunlight, water, and carbon dioxide into fresh oxygen through the same photosynthetic process refined across billions of years of evolution. Equally significant, though far less celebrated, countless microscopic phytoplankton drifting across the world's oceans continue producing a remarkably substantial share of the oxygen filling our atmosphere today, an overlooked marine contribution rivaling that of every forest on Earth combined. Scientists now monitor this delicate planetary system with unprecedented precision, tracking atmospheric oxygen concentrations from remote research stations, studying troubling oceanic dead zones where dissolved oxygen has fallen dangerously low, and documenting coral reef ecosystems whose survival depends entirely on stable, healthy oxygen levels within surrounding water. Even renewable energy research has found a place for oxygen, as hydrogen fuel cell technology produces pure oxygen as a valuable byproduct during water electrolysis, connecting cutting-edge clean energy development back to fundamental 19th century chemistry. From rocket launch pads to ordinary supermarket shelves, from deep ocean research vessels to quiet suburban households, oxygen remains woven invisibly into nearly every dimension of contemporary life. It is easy to forget, amid all this modern infrastructure, that every single application traces back to the same natural process, countless microscopic organisms quietly photosynthesizing, exactly as their ancestors did billions of years before human civilization, before language, before even the first stirring of complex life itself. To understand oxygen fully, we must travel back further than any human civilization, further than any written language, to a planet almost unrecognizable as our own. 4 billion years ago, Earth's atmosphere held virtually no free oxygen at all. Its skies glowed a hazy orange beneath volcanic haze, and its oceans steamed only with simple, single-celled organisms thriving without any need for the gas that would one day define nearly every complex form of life to follow. Then, roughly 3.5 billion years ago, ancient cyanobacteria began doing something extraordinary, converting sunlight, water, and carbon dioxide into simple sugars, releasing pure oxygen as a natural chemical byproduct. At first, dissolved iron throughout the ancient oceans absorbed this oxygen almost as quickly as it formed, creating the distinctive banded iron formations geologists still study today. But eventually, cyanobacteria began producing oxygen faster than the oceans could absorb it, and roughly 2.5 billion years ago, atmospheric oxygen began accumulating for the very first time in Earth's history. This transformation, known today as the Great Oxidation Event, triggered one of the most significant mass extinctions in our planet's long history, as countless anaerobic organisms, adapted to an oxygen-free world, found this new atmospheric gas genuinely toxic to their survival. Yet from this upheaval emerged something remarkable: organisms capable of harnessing oxygen for dramatically more efficient energy production, a biological innovation that would eventually enable increasingly complex, increasingly energetic forms of life. Oxygen accumulating in the upper atmosphere also formed a protective ozone layer, shielding Earth's surface from harmful ultraviolet radiation, and finally making life on dry land possible for the first time. Hundreds of millions of years later, during the lush, humid Carboniferous period, atmospheric oxygen concentrations rose even higher than today's levels, supporting dense forests and remarkably oversized insects whose massive bodies were made physiologically possible by that unusually oxygen-rich air. Those ancient forests, compressed slowly over millions of subsequent years, would eventually become the coal reserves that powered humanity's own industrial revolution, an extraordinary, unbroken thread connecting prehistoric photosynthesis directly to 19th century steel furnaces. It is a profound irony worth sitting with. Long before Priestley's burning lens, before Lavoisier's precision balance, before Scheele's quiet apothecary experiments, nature had already been producing, refining, and perfecting oxygen for billions of years. Humanity did not invent this element. We simply learned, remarkably late in our species' short history, to notice something that had been sustaining us all along. Today, astronomers scanning distant exoplanets search, hopefully for oxygen's distinctive chemical signature within alien atmospheres, treating its presence as one of the most promising possible indicators of life elsewhere in the universe. Perhaps that is the most fitting way to close this story. The very gas that once eluded humanity's greatest minds for millennia has become our clearest signal for finding life among the stars. Every breath you have taken while listening to this story connects you directly to cyanobacteria billions of years gone, to Priestley's astonished mice, to Lavoisier's final unfinished experiment. Look at the world around you differently now. You are, quite literally, breathing history.